In this presentation, I will be talking about fire safety engineering, particularly about its principles and applications in building fire safety design. To introduce fire safety engineering, we can say it's a relatively young engineering discipline. Nonetheless, it requires a high level of interdisciplinary knowledge because it combines a number of disciplines such as mechanical engineering, thermodynamics, chemistry, human movement, human behavior, toxicity, and so on. Therefore, it can be said that it's an advanced system of designing and assessing fire safety in building design. And its application requires good knowledge of calculation methods, professional knowledge, and engineering judgment in order to be able to select and apply the appropriate design methods. Fire safety engineering can be defined in a number of ways. However, the latest edition of ISO 23932 Fire Safety Engineering defines it as application of engineering methods based on scientific principles to the development or assessment of designs in the built environment through the analysis of specific fire scenarios or through the quantification of risk for a group of fire scenarios. When we talk about fire safety engineering, we can say that we always apply a type of fire risk analysis. There is two forms of risk expression in fire safety engineering. The first one is implicit, where the risk is hidden. That means that it's not directly expressed in our calculations, and this is usually tied with the deterministic method of fire safety engineering and application, where we use the worst reasonable case approach. In the other form, where risk is explicitly treated and is directly expressed, we can say that we are applying probabilistic or risk assessment approaches. When we look at the goals and objectives of fire safety engineering, it's a method of achieving an adequate level of fire safety in cases where the use of prescriptive approaches is not appropriate due to the specific or complexity of the design at hand. That means that applying prescriptive design methods would be either difficult or not possible because of the complexity of the building or the system. In fire safety engineering, we are not only selecting the methods of design and tools to prove that the design has sufficient level of fire safety, but we also select and define our fire safety objective, meaning that we are setting our goals for the design and deciding what is safe and what is not. Therefore, there is a risk of inappropriate objective definition, which means that we can end up applying or implement inadequate or insufficient fire protection measures, which essentially will compromise the level of fire safety for such design. The application of fire safety engineering is on the rise due to the use of modern architecture and design, which requires often an innovative approach to fire safety, and the complexity or other specific features of buildings such as high-rise buildings, atria, large open spaces, large assembly places, and so on. All of these require an advanced approach to fire safety design. Therefore, an increasing number of countries adopt and use fire safety engineering, some of which have already developed their own standards for fire safety engineering. We have international suite of standards, which is published by ISO with the main guidance document ISO 23932. Then another example is United Kingdom with its fire safety engineering standard suite BS7974, and also an example would be USA, which has a number of fire safety engineering related clauses in its NFPA 101. ISO 23932 has developed a framework for fire safety engineering application. We can see three main parts of its application. The first part, which covers the project scope, objectives, functional requirements, selection of analysis methods, and identification of performance criteria, is called boundaries of analysis, where we set out the limits of what we're actually going to be designing with the use of fire safety engineering principles. Then the second part, which is shown in the middle, actually means the evaluation of design through the creation of fire safety design plan, determination of design scenarios, application of the selected engineering methods, and evaluating if the selected performance criteria have been all satisfied. Once we have proved that our design is safe and all performance criteria have been satisfied, we can then document the design features in the final report, implement it, i.e. build the building and put all systems in place. And once the building is up and running, we have to execute fire safety management, which then focuses on running all the operations fire safe and monitoring any significant changes to the building, its use, or its systems so that we maintain the required level of fire safety throughout the building lifetime. When we start with fire safety engineering application, we first need to set and answer a number of questions. First of all, what is the objective of the construction project? Are we building a new building, changing an existing one, extending it, or changing a technology within an existing building? Subsequently, an important question of why or even if the fire safety engineering approach is required and appropriate. And here we need to answer why prescriptive approach is not sufficient, or it's the building too complex or has some specific features which do not allow for the use of standard prescriptive approach. What is the scope or an extent of the fire safety engineering approach? Are we just justifying for a number of deviation from the prescriptive guidance? Are we proving a level of safety for a very specific part of the building or technology? If it's applied to be applied for an entire building or a part of it, then we need to identify all of the involved or interested parties, for example, the investor, user, public within the neighboring buildings, authority having jurisdiction, insurer, and so on. And last but not least, we need to consider whether or not we have sufficient information for application of fire safety engineering approach. That means an in-depth knowledge of the building, its use, occupants, internal and external factors, and many more. The appropriateness of fire safety engineering approach can also be illustrated by this ratio of 85% to 15%, which appears to be the adequate ratio of standard prescriptive and engineering approach in fire safety design, i.e. the fire safety engineering approach shouldn't be applied in more than 15% of building design cases. Otherwise, the standard prescriptive approach has major flaws and cannot be used as it should be. As mentioned previously, there are always specific cases or building features that require fire safety engineering approach. This is usually possible or required in cases such as buildings with atrium, historical buildings, complex and combined use buildings, where we need to closely investigate these specific features on alone and in combination with other features of the buildings. We need to look at smoke spread, we need to look at evacuation and analyze these in detail. We need to realize the goal is not to recalculate design to satisfy all wishes of architects or investors, i.e. make possible what is not possible under standard prescriptive approach. When fire safety engineering is applied, there is a hierarchy of goal definition which is usually applied. The high-level goals are also called fire safety objectives. Then we identify or define functional requirements, which are more detailed elaborations of fire safety objectives. And finally, we need to define performance or acceptance criteria, which are thresholds or values which actually we use to prove that the functional requirements and therefore the fire safety objectives have been satisfied. We define fire safety goals in a number of areas. Most often we can divide these in 5 groups, such as life safety, property protection, business and operations continuity, environment protection, and heritage protection. We can illustrate the fire safety goal definition on a life safety example. The high-level fire safety objective may be defined as follows. The fire safety design shall be such that fire-related injuries to occupants away from the immediate areas of fire origin are minimized. That means we try to protect everyone that is not in the very close vicinity of the fire, and this may be then further broken down into a number of functional requirements, an example of which may be that the occupants are not exposed to untenable conditions due to elevated temperatures, radiation, toxic species, irritant species, or reduced visibility while moving along the paths of egress. This means that we try to protect, or we must protect, the occupants while evacuating by creating tenable conditions. And these tenable conditions are then quantified through performance criteria, which we may set as follows. Analysis method is the deterministic analysis. Performance criteria corresponding to conservative estimates are chosen, i.e. level of exposure to evaluate temperatures, radiation, and toxic species are set as shown on the screen. These values must not be exceeded in our design evaluation, and if we satisfy these performance criteria, we may consider the means of escape safe for the entire duration of evaluation. In order to evaluate our fire safety design properly, we need to select an appropriate analysis approach. The main 2 approaches which may be seen in the figure are comparative and absolute. Each of these then can use a number of analysis methods: qualitative, deterministic, and quantitative. These will be presented in subsequent slides. The first step we need to take is the decision about the comparative or absolute approach we're going to be using in our design. Comparative approach means that we have a baseline design which fulfills all the applicable prescriptive requirements, and against this design we're going to be assessing our engineer design. This means that we assume that fire risk is tolerable when all the prescriptive requirements are fulfilled, and therefore it's always necessary to have 2 designs. One, the baseline, against which we compare our engineer design. On the other hand, in the absolute approach, we consider design acceptable if all of the approved performance criteria are met, which means that we assume that fire risk is tolerable when the defined performance criteria are met. Therefore, it's necessary to have a set of clearly identified tolerable risk criteria, and we need to express these through numerical values which are known as performance criteria. Qualitative analysis is a special, simple, comparative analysis which is only applicable for small deviations from prescriptive requirements. Therefore, it's always necessary to compare against our design against a compliant prescriptive design and assess if the small deviations identified have been sufficiently compensated. Risk is treated implicitly in this case, and the deviations always have to be compensated for by additional fire protection measures. It's also necessary to assess the impact of all deviations on all fire safety objectives. even if the connections is not clear from the beginning, we always need to do this. The following matrix shows a possible way of evaluation of impact of one affected fire safety objective or fire safety measure on other ones. We may see that there may be primary, secondary, or even tertiary bounds between the objectives, and for example, extending escape routes has not only impact on the actual escape, but also on access for firefighters, and these prolonged distances may cause difficulties from the firefighting perspective. This way, we always need to check against every potentially affected objective and see whether or not it has been compensated, the deviation has been compensated for sufficiently. The deterministic analysis is a more advanced calculation analysis. It can be used in a comparative or absolute approach. The risk is expressed implicitly by the use of worst credible case scenarios. These worst credible case scenarios are considered the potential worst situation that may occur and given a reasonable probability of their occurrence. We therefore need to identify all relevant scenarios from the perspective of defined fire safety objective. Therefore, there is no such thing as a universally applicable worst credible case scenario, and we always need to identify worst case scenario for evacuation, for structural evaluation, for firefighting access, and so on. We have a wide spectrum of analytical tools available from simple calculation methods, for example for detection and activation, all the way to the advanced computational fluid dynamics fire models. Probabilistic analysis is the most advanced approach to risk analysis. It can be again used for a comparative or absolute approach, and risk in this case is expressed explicitly. We can divide it into semi-quantitative or quantitative risk analysis methods, where the semi-quantitative methods have broader definition of design scenarios, and part of the risk is usually expressed quantitatively, and the other part or component of risk, probability or consequence, is expressed qualitatively. Quantitative probabilistic analysis is the highest level of probabilistic analysis, fire risk analysis, and the main feature is the analysis of a wide spectrum of design scenario, as wide as possible, and therefore we apply usually probabilistic input distributions, reliability, availability, uncertainty treatments, and the calculations are quite complex, and therefore we need to specify the limits and the scope of application of such analysis. This slide shows how one of the components of risk may be quantified. We change either the frequency or consequence descriptors for a numerical value, which can be either point value or a range, to which we assess a group of scenarios. Fire safety design plan is a starting point for definition and assessment of fire scenarios. Due to occupancy and use specifics, the plan should contain information and design elements in a number of categories, which are shown as follows: fire initiation and effluent production, fire and effluent spread, constructions and compartmentation, detection, activation and suppression, occupant characteristics and evacuation, and firefighting action if relevant. All of these then will be used in formulation of our design scenarios and evaluated at a later stage. There are two categories of design scenarios. One concerning fires, we have design fire scenarios, and the other one is concerning human and their behavior, therefore we name them design behavioral scenarios. For design scenario specification, the first step is fire hazard identification, where the following specifics are considered. Internal, which comprise building occupancy type, processes and activities, construction and materials, equipments and furnishings, systems and technologies, fire protection and other systems, and the external factors or specifics, which usually comprise neighboring buildings, environmental hazards, and other factors that may affect the development or the design fire scenario from the external perspective. In this figure, we may see the process of fire hazard identification. We can see that part of the hazards can be addressed through prevention and the other part through mitigation measures. We can see that the hazards are divided in chronological order from even before the fire starts, then ignition and fuel hazards, enabling hazards which may worsen the fire conditions, and vulnerability hazards which are concerned the vulnerability of people, structure, and other parts of the design or the exposed targets which may suffer from fire. And subsequently we can arrive at the fire impact, i.e. outcomes, which is usually characterized through injuries, property damage, business interruption, or environmental damage. Fire scenario definition is a two-step process. In the first step, we describe our fire scenario qualitatively. This is described in ISO 16933 Part 1, and it concerns with identification and characterization of the aspects affecting fire development. So we put together our fire scenario as a number of steps in the effect of fire enabling and fire bearing elements that will then create our fire scenario. In the second step, we have to specify our design fire, which is the quantification of our qualitatively described fire scenario. This means assessing or attributing specific course of development of heat release rate or temperature profiles with time. This procedure is described in ISO 16933 Part 2, which is currently under development. This figure shows three fire scenarios, one for fully developed fire, the other one for smoldering fire, and the third one for sprinkler controlled fire. We can see the different courses of fire with time characterized by different heat release rates in time, and we can see how the effect of sprinkler protection affects the overall heat release rate. We can also see that the smoldering fire has very low heat release rate, but may be very dangerous from the perspective of smoke generation and affecting the escaping people. Behavioral scenarios, on the other hand, are concerned primarily with persons and their behavior in fire conditions. ISO Technical Report 16738 from 2009 recommends to consider the following elements. Primarily persons from the perspective of their number and distribution, if these people are awake and familiar, and what is their mobility, so how they will evacuate from the building, if they need assistance, if what the expected movement speed will be, and so on. And then also the building systems that may promote or affect the evacuation. This means, for example, the detection and alarm system, fire safety management and training, and spatial configuration, which may both help the evacuation or complicate the evacuation depending on the actual configuration. And also the fire scenarios, meaning fire development and effluent characteristics. That means concentrations of the toxic gases produced or smoke produced and its impact on visibility and walking speed reduction. This table shows an example of occupant characteristics groups. We can see different categories which are based around the occupant alertness, if they're awake, asleep, or if they need some specific medical care, which further may reduce their alertness. If the occupants are familiar or unfamiliar with the environment, with the building and its configuration, what is the occupant density, i.e. number of people per square meter, if it's high or low, and then what is the layout of the built environment, if it's complex or simple, and that also affects the evacuation and ability to navigate inside the building of the occupants. And then in the last column we can see a number of examples for these type of occupancy. As mentioned previously, we have a number of tools available in fire safety engineering, ranging from simple hand calculations through computer models, probabilistic studies and calculations, and experimental methods, which all may be used for evaluating of different parts of fire safety engineering design. This doesn't mean that we will always use the entire range. This depends on the complexity of the jobs we have to do, and also the appropriateness, ease of use, necessary simplification and approximations, compatibility with the defined fire safety objectives, and other factors that will affect the applicability of these different tools. You can also see a number of examples of books, journals, and the computer models and experiments that may be performed as part of fire safety engineering. In this slide, we can see the difference between deterministic and probabilistic approach in design and scenario evaluation. The deterministic approach compares two distinct values, and the load may never exceed the capacity. So it must always be less than the load must always be less than the capacity, and the difference between these two is considered margin of safety. On the other hand, the probabilistic capacity and load are expressed through distribution functions, and we can see there the overlap is possible as long the probability of overlap, i.e. the load being at the high end of the distribution and the capacity being at the low end is sufficiently low. Once we have evaluated all our design scenarios and we have proven that all of our fire safety objectives, functional requirements, and performance criteria are met, we can move to the documentation of the fire safety engineering design. Here we need to employ a detailed approach. We need to provide all the necessary information in the right extent and format. That doesn't mean to put everything into one document, but it needs structure and it needs to highlight the right amount of information in right places. And we need always to describe and justify why such conditions, why such input parameters have been used, what they mean, and how they affect the overall level of safety. Once we have our design approved, we can then move to the creation of fire safety manual and operation and maintenance manual, which are the base documents for the actual lifetime of the building, for its actual use and fire safe use. The final step in fire safety engineering is the implementation and fire safety management of our design. After the building or system has been constructed and installed, it is necessary to check the functionality of the individual fire protection systems and features individually and in combination to prove that the design as a whole is functioning properly and it performs all the functions required. We therefore need to introduce proper and thorough testing before the handover to make sure that before the building or the technology is open and running, we are sure that everything functions properly. Subsequently, we need to employ sound inspection and maintenance program to constantly check if all our systems and fire safety features are in place and performing their function as required. We also need to keep our fire safety documentation live and up to date to monitor all and record all changes and all modifications. This is particularly true for fire safety engineering designs, must be properly consulted with fire safety engineer and assessed in the context of their impact on the overall design, because even a small change may significantly impact the overall performance of fire safety engineer design. And we also need periodically check on the sum effect of so-called negligible changes, because a number of small or negligible changes added together may constitute a significant change and invalidate our design significantly. This concludes the presentation about the application and principles of fire safety engineering, and I thank you for your attention.